This is a video on section 14.1 where we're trying to really understand the idea between level curves and level surfaces. And at the same time, we're still trying to really wrap our heads around the idea of counting dimensions. Okay, and so I thought for this video we would look at an even problem number 58. Okay, there is lots to notice here. Okay, if we're just talking about terminology, okay, we've had some other videos up to this point where we've talked about implicit and explicit surfaces and those kind of ideas. So this is a follow-up to those videos. But I just want to remind everybody that, when we're looking at, for example, z is equal to f of xy, a function of two independent variables and one dependent variable z, that notice that there were three variables in play, x, y, z, so that makes us an element in R3, also known as space. Okay, but when you add a formula or an equation into the mix, like z is equal to f of xy, that drops us one dimension. So now if you take R3 and this formula together, we now are going to be in some sort of subset of three-dimensional space. Okay, and since we dropped a dimension, we're going to be in some sort of subset of R3 that we will call a two-dimensional subset of three-dimensional space. Okay, terminology is a little bit tricky in this section. Okay, so by extension, notice that what we are looking at in problem number 58, we now have a problem f of x comma y comma z, a function of three independent variables. And then there is an implied, and they've given you a formula for that function of three variables. And to make it more confusing, x is a variable, but it's not shown in the formula. So that says that the formula is independent of one of the variables. And then to make that even more confusing, there is a fourth variable that's missing. We'll call that t. So we're assuming that we've got this function t is equal to a function of f of x, y, and z. And if you could, for a minute, just imagine with me that t stands for temperature. So we've got three spatial variables, x, y, z for space, and we've got a fourth variable, t, for temperature. And together that makes four variables, four total variables. Okay, so we're in four-dimensional space. Okay, but once you have one equation, okay, but if you add a formula, you now are going to drop a 1D. So now we're in some sort of three-dimensional. So R4 with this single formula is a three-dimensional subset of four-dimensional space. And we still I have to think about what that means. Okay? So this is how we're going to try to wrap our minds around the problem. We are going to introduce the idea, as the textbook does, of something that's called a level surface. Okay? So do you see how that we still have, 1, 2, 3, 4 variables, right? We're in a subset of R4, but we're trying to figure out what this three-dimensional subset looks like. And the way we can get around that is by going one step further to knock out some more variables. So let's do that on the next page. Add a page below. Okay. So we had, as the book said, we have a function f of x, y, and z, and the function there was, what was the function? I'm sorry, y squared plus z squared. Y squared plus z squared. Okay. And I'm going to say that what we really have now is that t is equal to y squared plus z squared. Okay. And now let's start choosing. And by choice, I'm choosing to knock out a variable. And I'm going to choose to knock out the t variable, the temperature variable. So let's let t is equal to 1. Okay. And now what you can see is that we've got 1 is equal to y squared plus z squared, which was our function f of x, y, z. This was our function f of x, y, z. And we've chosen that fourth variable. We've selected it to be equal to 1. Okay. And now we've been reduced to an implicit function of the form f of x comma y comma z equal to some constant, where the function of those three variables is x squared, y squared plus z squared, and the constant is equal to 1. Okay? And we know that this is an implicitly defined function of this form, means that we are some sort of surface, 2D surface in three-dimensional space. Okay? So what we're getting at here is that when we had x, y, z and the variable t, that made us into R4, into four-dimensional space. But if you add the formula t is equal to y squared plus z squared, you're going to be a three-dimensional subset of four-dimensional space. And then if we go a step further and add another equation into the mix, example t is equal to 1, these two taken together will reduce us down to a two-dimensional subset of R4. And because that it's something two-dimensional, we can actually view that now. That two-dimensional subset of R4 is called the t is equal to 1 level surface of the function f of x, y, z equal to y squared plus z squared. Okay? And now we're down to some sort of two-dimensional subset. We can actually try to wrap our minds around what that is equal to. Y squared plus z squared is equal to 1. Seeing only two variables present there. Which means that in the yz plane, we are getting a circle of radius 1. Okay? And because notice that the x was missing, what that means is that we get a circle of radius 1 for each value of x that you pick. So let's add another dimension. Here's x, the x dimension. And for every value of x that you pick, you're going to get a circle of radius 1. Pick a value of x back here, and the negative values of x, you'll get a circle of radius 1. Put all those together, and your 2D subset of R4, aka the t is equal to 1 level surface, is the surface of the cylinder. Okay, so this question right here, all they asked you to do was to find an example of a level surface. Okay, we found the t is equal to 1 level surface. Okay, you could have chosen to find the t is equal to 2 level surface. You would have taken the function f of x, y, z is equal to y squared plus z squared. You would have taken that function and set it equal to 2. Let's say 4, just for sake of ease of computation. And then looked at y squared plus z squared is equal to 4, which would have been a circle of radius 2 for every value of z. Right? And so the t is equal to 4 level surface would have been a larger cylinder. Okay? So the way you can, if you want to visualize some of these level surfaces, you just need this, in Mathematica, you can say contour plot 3D, and you can put your function of three variables, y squared plus z squared, and there is an x missing. And then you can tell it to choose which level surface to pick. Let's pick t is equal to 1. Okay? And then plot this in three-dimensional space, because we were looking at when we're plotting this surface, it's a subset of R4, but it's also a subset of R3 also. So -2 to 2, plot y from -2 to 2, and let's plot z from -2 to 2. So we fixed a temperature T, so that knocked us down to three-dimensional space, and now we're having a formula in that three-dimensional space that should plot us a subset of that three-dimensional space. So there is your T is equal to 1 level surface. Okay. If you want to look at another level surface, you could look at y squared plus z squared equal to 4. And there is another level surface. Okay. So that's why I like to think of these functions of three variables. I like to think of them as temperature functions. It helps me wrap my mind around these. That pick a point in three-dimensional space, plug it into the function, and that will tell you the temperature at that point in space. And once you select a specific value of T to make the level surface, everything that is at the same color is at the same level of T. So everything in orange is at the level of T is equal to 1. Everything at blue is at the level of T is equal to 4. Okay. And I've got a demo over here that kind of does this quite a bit quicker. You can see here that what we're going to do is we've seen one of our level surfaces was a cylinder, and now let's start changing the contour. Okay, we're looking at y squared plus z squared equal to 2 now, so your level surface is a temperature, a cylinder of radius squared of 2. Those are all the points that are at the same temperature, 2. Change to a contour temperature 3, and everything on a larger cylinder is at the temperature 3. So this is the temperature T equals 3 contour surface of the temperature function. Okay, so I hope that that video helps with some of the terminology and shows maybe kind of what you could do with the handwritten solution to the homework problem. And also, if you choose to use Mathematica, it's you can find the download instructions on our course website, and it's pretty straightforward, small number of commands to get pictures of these things. All right, so hope that helps.